Last time, the big result was this theorem here: projective varieties are separated, hence they are varieties. Okay, so we did that by checking that the diagonal was closed. We used the segue embedding. Okay, so the next big property about projective varieties is the sort of compactness. Now, similar to the situation with separated, the traditional idea of compactness is not quite right for the Zurich topology. So let's do some remarks to see why that's the case. So let's recall that a Noetherian topological space is always compact. I think we had that was an exercise in the first chapter or something. That includes all pre-varieties are Noetherian topological spaces. So the idea of compactness in the traditional sense is not useful. Okay. But here's the thing we actually want to capture. So affine varieties of dimension greater than 0 are not compact in the classical topology. So think of like Cn, the affine space Cn is not compact. Compare that to projective varieties. So projective space, for example, these are compact in the classical topology. I'm not sure if we gave a proof of that or not, but you should kind of think that in your head at least. Okay, so somehow we want to capture the difference between affine varieties and projective varieties, this compactness in the classical topology, but we want to have an algebraic version of it that works over any field and makes sense that way. Okay, so let me give you just a little lemma from topology to give us some motivation. This is going to be kind of analogous to what we did with separatedness. Remember, we gave a different characterization of Hausdorffness that used a product, and it ended up being different than Zurich topology because the product of varieties is not the same as the topological product. There's going to be something very similar to here. All right, so here's the lemma. So C is compact if and only if the map pi from C cross Y down to Y, so just the projection onto the second factor, is a closed map for all Y, for all topological spaces Y. Okay, and what do I mean by saying a map is closed? So let me just write this down. So recall a map, a function, a continuous function, right? So this is a continuous. Is closed if pi of z is closed for all z in the domain. All closed subsets z of the domain. This is a lemma about general topology, not about algebraic geometry, but let's do the proof anyway, just because I like it. All right, so let's do the forward direction first. We're going to use the characterization of compactness that every infinite sequence has a convergent subsequence. That's equivalent to being compact. All right, so let's assume that we have a sequence, so y that converges to y, yi that converges to y, where the yi's are in pi of z, where z is some closed subset of c cross y, and we're assuming c is compact. We just need to show that pi of z is closed, so we just need to show that y is in pi of z, and then we'll be done. Okay. Well, the fact that the yi's are in pi of z means there exists some ci's, so that ci yi, the pairs of ci yi are in z. All right, that's just the definition of the projection. Okay, now by passing to a subsequence, we can assume that the ci's actually converge to C, because C is assumed, the capital C is assumed to be compact. All right. Hence, we see that a Ci yi, well, okay, the yi converges and the Ci converge, so so the sequence in the product also converges. Okay, so then this has to be in Z because because Ci yi, these are all in Z, and and Z is closed, right? Okay, but if a C, Y is in Z, then that means that Y is in pi of Z. So we're done with that. Let's do the other direction. So let's take C cross R and assume that the projection down to R is closed. All right, and we'll take now let's say we're given any sequence in C, and we're going to take pi of the closure of that sequence together with 1 over I. Okay, so here's an arbitrary sequence in C. We're going to add in some 1 over i's and then take the closure of that sequence. Now, of course, 1 over I, the set of all 1 over i's, is going to be contained in that image there. But actually, we're assuming that pi is closed, so actually the closure is contained in there, which means that we have 0 in here. Okay, so 0 is in this image, then that means that there exists some element C comma 0 in this closure. All right, okay. So if Ci is in this closure here, then that tells me that by passing to a subsequence, we can have a Ci 1 over I converges to C0. Okay, and then of course this tells me that Ci converges to C. The projection onto the first factor is continuous, so it preserves limits. All right, and so we have that our original sequence Ci has a convergent subsequence, so C is compact. All right, so we just proved C is compact is equivalent to the projection C cross Y to Y is closed for all Y. All right, let's get back to algebraic geometry. So our goal is going to be to prove that projective space or projective varieties have this property on the right here, that the projection of projective variety across with any variety projected onto the other variety is going to be closed, a closed map. Okay, and we're going to get something different than what this lemma says, because the product in the category of varieties is not the same as the topological product, but it'll turn out to be the thing we want. All right, before we can prove the full lemma, we have an easier case that actually contains most of the hard work. So here's the lemma, the projection map. Pi from Pn cross Pm projecting onto Pm is closed. All right, so the full thing, we really want Pn to be any projective variety, and we want Pm to be any variety, but we'll extend to those cases in a minute. Before we do the proof, let me just give you this remark that we skipped a little while back, but we're going to need it now. So it says the projective vanishing locus of f, where f is a homogeneous polynomial, is equal to vp x to 0 d times f, x1 to the d times f, and so on. And the point now is that you've increased the degree of f, right, by multiplying by x I to the d. Okay, and the consequence is any projective variety can be written as a vanishing locus of homogeneous polynomials, all of the same degree, right? If there was different degrees of your homogeneous polynomials, the ones that were a smaller degree, you could just bump them up by using this this little trick right there. Okay, so now we're ready to do the proof. So let's let Z be any closed subset of Pn cross Pm closed. All right, so Z is the vanishing locus of F1 through Fr, where the Fi are homogeneous of degree D in the Segre coordinates, Zij. So remember, in the last lecture, we showed that the product of two projective spaces is a projective variety using the Segre embedding, and the Segre embedding had these coordinates Zij. Okay, but also remember that the coordinate Zij corresponds to xi, yj, where xi was one of the coordinates on the Pn and yj is one of the coordinates from Pm. All right, so that means that we can think of Fi as a bihomogeneous polynomial of degree dd in x0 through xn and y0 through yn. Okay, maybe I don't want parentheses here. All right, so remember, so once again, x0, the x's are the coordinates on Pn, the y's are ym here. Y's are coordinates on Pm, so you can think of these fi's as a polynomial where each monomial has a degree d in the x's and also degree d in the y's. Okay, so now let's let A be a point of Pm, and let's let Gi be Fi of blank comma A. So we're thinking of this as just a polynomial in the x's, right? You plugged in some value for all the y's, so now you just have a polynomial in x's. All right, and so we want to think about when A is in the image of Z under the projection. All right, so let's write this. So A is not in the image of Z. That's exactly saying there is no x in Pn with x comma A in Z. That's just the definition of the projection. Okay, but that's the same thing as the vanishing set of G1 through GR is empty. Right, if you're looking at well, so a point XA is in Z if and only if all the FI's vanish on it, but that's the same as saying the GI's vanish on X, so that's what we got here. Okay, now if we have the vanishing set being empty, the only way that happens is if the irrelevant ideal x0 through x1 is contained in the radical of the ideal of the G's here. All right, so that was our theorem here. The vanishing set is empty if and only if the irrelevant ideal is contained in the radical, like this. Okay, and let's just now apply the definition of the radical. So there are ki, so that xi, ki are in the ideal generated by the G's. Okay, and finally, this is equivalent to if you take the polynomial ring and look at degree k for a k large enough, then that will be contained in the ideal. All right, for k large enough. Okay, in fact, you could take, for example, k to be equal, k1 or k0 plus all of the kn. Should be big enough. What's the idea here? So any monomial here has to have, well, it can't be the case that all all of the variables have degree less than the ki's, because then it would have a degree less than this k down here, right? Okay, so any monomial has to have xi to the ki for some, at least, and then that would show that it's in the ideal, right? Okay, good. Okay, and this is the same as saying that all the degree k homogeneous part is equal to the degree k homogeneous part of this ideal. Okay, right? Because the if you're taking the degree k homogeneous part of an ideal, I just mean that I'm intersecting with this k x0 through xn sub k, right? So that's clear. All right, so now let's look at the following map. So we're going to define a map called capital F subscript k that takes k x0 through xn k minus d. We can assume k is greater than d. R copies of that and then maps into kx through xn degree k things. And what does it do? Well, it just takes some polynomials h1 through hr and maps them to the sum of gi, hi. All right, okay, and the image of this is precisely the ideal generated by the GIs, right? At least in degree k. Okay, but we just said that image is the whole thing. So we know that fk is surjective. All right, now let's remember here that this fk is a map of finite dimensional vector spaces. So we can write a matrix for it, right? And notice that the matrix for f has entries which are polynomials in A. Right? How does this map work? Well, this map is basically just defined by these multiplication with these GIs. But what are the GIs? Remember, the GI is just equal to fi blank A, so you just have a bunch of A's plugged in there. Yeah, and those are polynomials, right? Okay. All right, and then the basis is given by like monomials in X or something. So you can write a matrix for fk that just has entries that are polynomials in A. Okay, so now fk is surjective. This will be equivalent to at least one maximal minor of the matrix for f is not 0, right? Okay, in other words, we need to say that A is not in the vanishing set of the maximal minors. Right, because the entries of the matrix are polynomials in A. So if you take a maximal minor, that will again be a polynomial in A. So it makes sense to say that I want to not in A. If A is not in the vanishing set of the maximal minors, that's equivalent to the map being surjective. All right, okay, but now we have what we want, right? We've proven that, going back up here, A is not in pi of z. It's the same thing as A is not in the vanishing set of the maximal minors. Okay, so that shows that the vanishing set of the maximal minors is exactly pi of z. So it's a closed set. So pi of z equals vanishing set of maximal minors closed, which is what we wanted to show. This result is sometimes called the main theorem of elimination theory. So why is that? Well, you can think of it like this. We have some equations in x and y, and what we've done now is we've gone through and now gotten some equations down here that are just equations in y that have to be satisfied with no reference to the x's. So we started with equations in x and y, we've eliminated the x's, and now only have equations in y. And this theorem is saying that this is always possible for homogeneous systems of polynomials. Okay, so that's kind of nice that way. So now we are ready to prove the result that we were shooting for, that the projective varieties have this kind of universally closed property. So the projection map pi from Pn cross y mapping to y is closed for, I guess I should say this correlation is just for projective space, not for any projective variety. We'll get to that in a minute. This is closed for any variety y. Alright, so let's do the proof. First, let's do the case where y is affine. So we'll have y contained in AM, and we'll do the more general case in a minute. We can think of an affine space as being contained in a projective space in kind of the way that we're used to, right? Now let's let Z be the closed subset of Pn cross y. Closed. And then let's also think about the closure of Z in Pn cross Pm, right? So where I'm thinking of y being included in Pm as we said, then you can take the closure of Z there. All right, now let's think about what is the image of the projection of Z. Well, Z is the same as, you can just take as closure and intersect with Pn cross y. All right, Z bar was just defined to be the closure of Z when Z was originally contained in Pn cross y, so that's the same thing. Okay, and then just by a little set theory, so you can think about this, that's P of Z bar intersect y. Okay, now P of Z bar, this is closed this is closed in PM by the result we just barely proved. Okay, and then if you take a closed set intersect with y, now this is exactly closed in y using the subspace topology, right? Okay, and so pi of Z is closed in y. That's exactly what we want. All right, so now we should check what happens if y is any variety. But this is not a problem, because checking whether something is closed is kind of a local condition. So we can just use an open cover by affine varieties. All right, so I'm not going to write anything more. You can fill in the details if you want, but the idea is you take this open cover, and then you can check that if you take the closed subset and intersect it with each piece of this open cover, the projection will be closed, and then you put that all together and find out the whole thing is closed, right? Okay, so I'll let you fill that in if you want to. All right, let's give a name to this property. So definition of variety, X is complete if for every variety Y x cross y mapping down to y is a closed map. All right, so this complete property is going to be our replacement for compactness. All right, so let's just summarize what we know so far. So we know that Pn is complete. What else do we know? So here's a nice fact. Every closed subvariety of a complete variety is also complete. Okay, this is not too hard to check. I mean, so suppose we have x prime contained in x as a closed subvariety, and let's assume x is complete. Then you can take x prime cross y. That will be closed in x cross y. And then if you take any closed subset of x prime cross y, it will still be closed in x cross y. So then when you project it down to y, the image of z and y here will be closed, but it's easy to see that this diagram commutes, right? So so it'll be closed here too. Okay, so you can think about that. All right, but the corollary of part B here is that now every projective variety is complete. All right, so that was our goal. Let's contrast this with the case of affine space. So let's look at A1. So A1 is not complete. So let's see an example where the closed property fails. So if we look at A1 cross A1 projecting down to A1. So just draw my picture of A2 here, and it just projects down onto one of the factors. Let's take a closed subset. Z equals the vanishing set of x, y minus 1. So you get this kind of a hyperbola thing, right? All right, so this hyperbola is exactly z. This is a closed subset of the product. But what is this image here? So the image of z is just going to be the affine line minus the origin, right? So the origin is pi of z is not closed. All right, so that shows that A1 is not complete. Now, the way we fix this, so remember if this vertical line right here were P1 instead of A1, then there'd be kind of a point at infinity here. So this line would intersect some point at infinity, and that would map down to here and make that set down there closed. Okay, but it didn't work with the affine line. So that's kind of the intuition behind the name complete. Somehow the affine space is missing some points at infinity, but the projective space is complete. It has all the points. Okay, let's make a remark here that there are complete varieties that are not projective, but they are kind of hard to find. Are not projective, but they're difficult to find. So, so in this class, you can basically think of projective and complete as being the same thing. I don't think we'll ever see one of these complete non-projective varieties in this class. So this completeness is really the property of projective space that's most important. You know, there's not so many theorems that are true for projective varieties, but not true for complete varieties. That's pretty much completeness is the important property. All right, let's now prove a nice corollary it says let f from x to y be a morphism, and then if x is complete, then the image f of x is closed. Alright, so this is some analog in topology of the fact that the image of a compact set under a continuous map is closed. Alright, so let's do the proof of this. It's not too hard given what we have. So we have the graph of f contained in x cross y is closed. Okay, but then f of x, the image of x under f, so yeah, f of x is just equal to the projection of the graph, right? All right, so this is closed by completeness of x. Completeness of x. All right, and remember the graph was closed. I believe we proved that back when we were talking about the separated property. So you need x and y to both be varieties. So you need or at least one of them to have the graph closed. Okay, let's now prove this corollary, which is an analog of a fact from complex analysis. So let x be connected and complete variety. Then the ring of global functions, OX, X, so this is regular functions that are defined on the whole space, is just equal to k, the constants. Constant functions only. Okay, let's see how completeness gives us a proof of that. So if we have any global function, x, then that will give us a map from x to a1. So we saw how global functions give morphisms. All right, and if you have one of them, you get a morphism to a1. All right, but now you can think of a1 as being contained in p1, right? Let's think about, and let's go ahead and call this map phi. We'll give it the same name as the regular function. That shouldn't cause any confusion. Let's think about what the image could be. So phi of x, first I say it can't be a1 because phi of x has to be closed in p1. Right, because of our previous corollary that we just proved, if x is complete, then its image has to be closed. All right. Okay, and it also has to be closed in A1, and we know the only closed subsets in A1 are the whole space, the empty set, and finite sets. So that tells me that phi of x is a finite set. It's definitely not the empty set. Okay, and then we also, just from general topology, we know that the image of a connected set is connected. So so phi of x has to be connected. So that means phi of x is a single point. All right, so if the image is a single point, that means the function is constant. So there's only constant functions. All right, so compare this to affine varieties. For affine varieties, the global functions were isomorphic to the whole coordinate ring. So there's lots of global functions. For projective varieties, there's not many global functions. There's only the constants. All right, and as I mentioned before, this is an analog of a theorem from complex analysis. there's the only holomorphic functions on a compact complex manifold are constants. All right, so now we're going to do another kind of a useful construction called the Varieties embedding. All right, so we're going to pick N and D, and we'll let F0 through F capital N be some polynomials in the ring with the n+1 variables. And what are they going to be? They are the n plus d choose n minus 1 monomials, degree d. All right, so I mean, for example, if we had n equals 2 and d equals 2, then this is just something like you have x squared, xy, and y squared. Okay, and we're going to find a map, let's call it f, from Pn to P capital N, where capital N is this number here, and it's given by x maps to f0 of x all the way up to fn of x. Okay, and this is a morphism because remember we had the theorem a while back that if you have a bunch of polynomials all homogeneous of the same degree, then you can use them to define a morphism to a projective variety. So that's what we're doing here, and you can check that the simultaneous vanishing locus of all these is radical contains the irrelevant ideal. So it actually defines a morphism on all of Pn. Okay, and what we claim is that this is actually an isomorphism onto its image. Onto its image. How can you see that? Well, we can look at we can try and find the inverse. Let's just find the inverse on an affine patch. So let's assume that we are on the an contained in, or a capital N contained in Pn, where the coordinate corresponding to x0 to the d is not equal to 0. Okay. Well, this also tells me that the x0 is not equal to 0. So let's look at the affine patch where x0 equals 1, and we'll look at this map from an to an. This will be the restriction of f inverse. Okay, so what do we have to do? We just have to give n regular functions here, and we do it like this. We put xj is equal to xj times x0 to the d minus 1 divided by x0 to the d, right? Because if we're setting x0 equals to 1, this is exactly equals xj, and this is a quotient of 2 degree d monomials. So that's a quotient of two of these coordinates, 2 of these f's here, and you get back the point xj just like you wanted to. Okay, and then you do this on all the standard open patches and paste them all together, and you get the f inverse. Okay. All right, so this f here is an isomorphism onto its image. That's the point here. Okay, the advantage of the Veronese embedding is that now degree d polynomials now become linear polynomials in the Veronese coordinates. Okay, so in a minute we'll see an example when that might be useful. First, let's just look at some examples. So if you pick d to be equal 1, the degree 1 Veronese, that's just Pn to Pn is the identity. Right, you just take all the degree 1 monomials, which is just x1 through xn, so you just get the identity. For n equals 1, so then we're going to have a map from P1 up to PD, and it will just look like this, right? It will just be x, y maps to x to the d, x to the d minus 1y, just like this, all the way up to y to the d. In fact, I think I gave you an exercise of the case where d equals 2 earlier in the semester, where we looked at this Veronese map. All right, so that's just to get you thinking about some examples for small n and d. Now let's do the example where we use the Veronese to prove something interesting that I promised you. All right, so let's let x in Pn be a projective variety, and let's let f be homogeneous. It should be non-constant too. Then x, subtract off the vanishing of f, so x minus this hypersurface, will be an affine variety. All right, let's do the proof. Let's do the sort of easiest case first. If f equals x0, then x minus the vanishing of f is just equal to x intersect u0, where u0 is this standard affine open set that we talked about earlier. This is the set where well, x0 is not 0, right? And we checked earlier that that was an affine. This is actually isomorphic to an. u0 is isomorphic to an, so x is now a closed subset of an. All right, so that's an affine variety. If f is any linear polynomial, so degree 1, we can use a projective automorphism. Okay, to move that linear polynomial to x0, right? There's no special lines in Pn; all lines are the same. So anything that is true of f equals x0 can be true of any other linear polynomial. Okay, and if f is higher degree, then we use the Veronese invariant embedding and get the result. So this is exactly what I was saying earlier, that the Veronese turns degree d polynomials into linear polynomials. Just to be kind of completely explicit about it, let's look at x inside of Pn, and then we'll have the Veronese invariant that takes it to P capital N. If we had f as the sum of, let's say, ai xi, where I is some multi-index, so xi represents some monomial, then maybe I'll write f bar to be the sum of ai, and I'll write x subscript I, where x subscript I are the Veronese coordinates. Right, so each x subscript I is now just one single variable, but it corresponded to a monomial of higher degree. So now so the point here is that v of f intersect x is the same as v of f bar intersect x underneath these under these inclusions up here. All right, so I think that's all for today, and that's the end of this chapter.